Hello there and welcome back to Background Children. In this video we're going to be looking at circuit symbols, charge and current, and this is part 1 of 4 for the electricity topic, so let's get right into it. Electricians draw circuit diagrams to show standard components. Some of these you will be familiar with from your younger years, so standard components are just things which you can wire up to form a circuit with. We're going to go through these one by one. I recommend that you learn all of them because they could come up in the exam. In the exam they might even ask you to draw a circuit with many of these in, so it's a good idea to know what they all mean. This is an open switch. This is a closed switch. This is a cell, a battery, a diode, a resistor, a variable resistor, a light emitting diode, a bulb, a fuse, a voltmeter, an ammeter, a thermistor, and a light dependent resistor. If you're following along in your revision workbook, complete task 1 and pause the video. Okay, so it's great knowing what all of those symbols mean, but what actually are these components? Well, let's take a look. Lamps are used to emit light. They involve an energy transfer. What is the energy transfer involved? Well, if you've been watching the previous videos, you will know that in a lamp, electrical energy is converted into light energy. Switches control whether or not a current can flow through a circuit. So if you open a switch, whatever the circuit does will stop because the electricity won't be flowing. The circuit will be incomplete. If you close the circuit, you will complete the circuit, and whatever the circuit does, well, it'll work again because the electricity will be flowing. An ammeter measures the current in the circuit. You connect an ammeter in series in the circuit. In series, what does that mean? We'll have a look. Okay, so if you have a circuit with a cell, with a switch, and with a lamp, like that, and you want to connect an ammeter to measure the current, well, what you would do is you would open the circuit up, draw in your ammeter into the circuit, and make sure that the ammeter is connected in the same loop, in the same wire sort of setup as the other things in the circuit. That's in series, so there's lots and lots of things on the same loop. Like a series of episodes, there's lots and lots of episodes. In a series circuit, there's lots and lots of components in the same loop. A voltmeter measures the voltage of the circuit. You connect this in parallel. So again, let's just say you have the same circuit where you have a bulb, you have your closed switch, and you have your cell. Well, let's say you wanted to measure the potential difference or the voltage across the lamp or the bulb. What you would do is you would connect your voltmeter in parallel. And what that means is that the voltmeter isn't on the same loop, it's on a new loop, a loop of its own. And what the voltmeter will do is it will measure the potential difference across the component which you connect it to, because voltage is more or less the same as potential difference. Diodes make sure electricity only flows in one direction. So if you put a diode in your circuit, the current will go one way and it won't be able to go the other way. LEDs are diodes which emit light. They're very efficient and are revolutionising the way we light our streets. So you have lots of LED lamps in the street now, rather than the old incandescent bulbs. So the old-fashioned bulbs which lit with streets, well, they're starting to die out, and LED street lights are much more common now, as well as in traffic lights and in our houses as well. Resistors resist the flow of charge through a circuit. They resist a current. So if you put a resistor inside your circuit, what you'll find that it's harder for the current to get through, and it costs energy for that current to go through that resistor, so the potential difference will be spent on the resistor. Fuses blow when a current which is too large passes through. If the current is too high, the wires can get hot and cause a fire. So fuses prevent fires. Think about it like this. Fuse starts with F, so does fire. Fuse, fire. Fuses stop current, not voltage. And it is a high voltage that can kill you. A fuse works by having a thin wire which is burnt through when too high a current passes through. So fuses don't stop you getting electric shocks. They stop fires because they prevent too high a current from becoming taken from the supply. LDRs, or light dependent resistors, and thermistors adjust their resistance depending on the environment. So this is something that my physics teacher taught me, and I think it's very useful actually. It's BURD and TURD. These are sort of little, what do you call them? I can't remember what you actually call them. Little ways to remember things. There is a special word for that, but I can't think of it at the minute. BURD, brightness up, resistance down. BURD works for light-dependent resistors, and if you remember this simple thing, you will pass these sorts of questions. So BURD, brightness up, resistance down. For light-dependent resistors, if the brightness increases, the resistance decreases. Okay? TURD, that stands for temperature up, resistance down. TURD works for thermistors, and again, remembering this is key in your exams. So when it comes to light-dependent resistors, higher brightness, lower resistance. When it comes to thermistors, higher temperature, lower resistance. So it's the opposite of whatever the environment's doing. If the brightness goes up, the resistance goes down. If the temperature goes up, the resistance goes down. So this is just a quick reminder of what we were looking at before with the series and parallel. Series circuits are as shown. They are circuits where different components are connected on the same wire. So we'll have the cell, we'll have a open switch in this case, and we have a bulb all connected on the same loop. That's a series circuit. Parallel circuits are as shown. They're circuits where different components are connected on different wires. Complete task number 2 in your electricity workbook and pause the video if you are following along. So, quantitative electricity. Well, quantitative is all to do with numbers. We're going into the maths bit now. Little bit of a pre-warning for you. A little bit like energy, there are a lot of equations to learn for electricity. Lots of units, lots of definitions. It is quite difficult, but we'll get through it, okay? We'll go through it slowly. We'll go through all the units, all the definitions, and there's nothing to worry about. So some of these include voltage, current, resistance, charge, and power. So, firstly, potential difference or voltage and the volt. For electrical charge to flow through a closed circuit, the circuit must include a source of potential difference. Can you think of any sources of potential difference? Well, I'll tell you some. A battery, or a cell, or a dynamo, or if you're thinking much bigger scale, you can think of power stations. Potential difference is measured in volts. So the unit for potential difference, or the unit for voltage, because potential difference and voltage are the same thing, is the volt. So that's quite an easy one to remember. Voltage is measured in volts. Potential difference is also known as voltage. Voltage is the energy per unit charge. So that's what voltage is. Voltage is the energy per unit charge. So if you think of something which has charge, like an electron for example, voltage is the energy which that unit of charge has. A volt is equivalent to 1 ampere of current travelling through 1 ohm of resistance. So what actually is a volt? What is the unit of a volt? Well, it's 1 amp of current, or 1 ampere of current travelling through 1 ohm of resistance. For a current to flow, there must be a source of potential difference. When there is a source of potential difference where energy is being transferred into electrical energy like a cell or battery, a current flows. Current is the flow of charged particles and is measured in amps or amperes, and that's given the symbol A. An amp is equivalent to 1 coulomb of charge travelling in 1 second. So that's the definition of the unit amp. Just like mass, charge is it's a property of matter. It's just something which matter has, something which particles have. Charge is like any other quantity in physics, but it is more complicated because you can't really see it. You just have to believe that it's there, you know? A little bit like mass. It's like describing mass. Well, everything has mass. Well, everything has charge. Some things have zero charge, but it's just a property of things. So charge is measured in coulombs, and 1 coulomb is simply an amount of charged particles, mainly electrons, but it can be ions in a solution as well. The definition of the coulomb is equal to the quantity of electricity conveyed in 1 second by a current of 1 ampere. So 1 coulomb, the unit for charge, is 1 second of electricity where there is a current of 1 amp flowing. Resistance is the opposition to a current. So resistance is something all components have. There is nothing which has no resistance. Every material, every component in a circuit, everything has some sort of resistance. The definition of resistance is the opposition to current through material. Resistance is measured in ohms, which is given the symbol omega, shown here. And 1 ohm is equal to 1 volt being dissipated when 1 ampere passes. So an ohm, the definition of 1 ohm is 1 volt being spent, if you like, when 1 amp passes. Can you come up with pictures or a diagram or an analogy to represent voltage, current and resistance? Well, have a go in task 3 in your electricity workbook and pause the video now if you are following along. Okay, so you could, for that task, have said that lorries moving are the current, the load which they are carrying is the voltage, and the speed bumps and corners in the road are resistance. When current passes through something with resistance, work is done, and this brings us on to one of our next equations. But for now, complete task number 4 in your electricity workbook, if you're following along, and pause the video. Okay, so here is the table which represents all of those quantities, the units and the symbol which they are given. So this is, again, it's something which you just have to learn. It's a bit of a long process learning all this, but you know, it's just like when you were young and you were learning your times tables, you just got to keep going over it and eventually it'll stick. So quantity, current, definition. Electric current is the rate of flow of electric charge. Unit, ampere, or amps for short, and the symbol for that unit is A for amps. The symbol for current is I. So in equations you might see V equals IR for voltage equals current times resistance, and you're just given these symbols. So voltage, well, that is the work done in moving a unit charge between 2 points. The unit is volt, V, and the symbol is V as well. Resistance is the measure of opposition that the substance has against electric current. That's given the unit ohm, or omega for the sort of shorthand for ohm, and the symbol R. Charge, well, the definition of charge is a quantity with positive or negative magnitude. It is just a property of matter. Some things have charge, some things don't. And the unit of charge is the coulomb, or C. The symbol for charge in equations is Q. So when it comes to measuring voltage and current, you connect an ammeter, which we have studied before. We've already looked at what the symbol for an ammeter is. Well, that's it there. It's an A inside a circle. It's important that you connect this in series. In series means that the ammeter is in the same wire as other components, which we already know. So this would be how you connect an ammeter to a simple circuit. Let's say you have 2 lamps or 2 bulbs, and you have 2 cells at the top, and you want to measure I was about to say resistance there. You want to measure the current in the circuit. To measure the current in the circuit, you just connect an ammeter in series, and this is shown here on the same loop as the bulbs and the cells. To measure voltage, you connect a voltmeter. It's important that you connect this in parallel. In parallel means it is in a different wire to the component which you are measuring the voltage for. It measures the potential difference across the component, so it's connected to both sides of it. Again, this is how you connect a voltmeter to a simple circuit. So let's say you wanted to measure the potential difference across one bulb. What you would do is you would connect the voltmeter across the bulb. So you would connect one wire on this side, connect the other wire to this side, and then that would measure the potential difference across that bulb. So next we are going straight into the equations, and we are learning the first equation, which is charge. The equation for charge, Q equals IT, charge equals current times time. And this equation you do need to learn. Let's have a look at a worked example to see how you would use this equation. If a current of 3 amps is flowing to a car lamp for 5 seconds, what is the charge delivered? State the unit in your answer. Well, charge is equal to current times time. First of all, write out your equation. So the charge is equal to 3, because it's 3 amps, multiplied by 5 seconds. The charge is 15. Since charge is measured in coulombs, our final answer is 15 coulombs. A device requires 500 coulombs of charge to function correctly. If wired to a 9 amp supply current, is 200 seconds enough time for the device to function correctly? Well, in this case, what we are trying to work out is the amount of time which would be needed. So we're going to rearrange this formula for time. We want to work out time. So first of all, write out our equation. Q equals IT. Charge is current times time. 500 is equal to 9 multiplied by t. Well, we're going to move the 9 to the left-hand side. We're going to divide both sides by 9 to get t by itself. And once we've done that, we'll get 55.55 seconds. So if you give this device 200 seconds, the charge transferred will be enough, because it only takes 55 seconds to charge. If you give it 200 seconds to charge, you're going to give it enough electrical energy for it to function correctly. Complete task 5 in your electricity workbook if you are following along, and pause the video. Right, so our next equation is that voltage is equal to current times resistance. V equals IR. Again, it's one of the ones that you need to know. Voltage is measured in volts, current is measured in amps, and resistance is measured in ohms. Let's have a look at how you would use this equation. In a circuit, the current is 3 amps. A component has a resistance of 9 ohms. Calculate the voltage across the component. Well, firstly, we're going to write out our equation. V is equal to IR, or voltage is equal to current times resistance. Voltage is equal to 3 times 9, because we have 3 amps and we have 9 ohms of resistance. So the voltage is 27. Voltage is measured in volts, so my final answer is 27 volts. In a machine gun, a DC current, or a direct current, we'll cover this in a little bit, powers the motor which fires the bullets. The DC current has a supply of 12 volts and has a current of 90 milliamps. Calculate the resistance of the motor. So again, first thing we're going to do is write out our equation. V equals IR, or voltage is current times resistance, and we're going to plug our numbers in. Well, our voltage is 12, because it's 12 volts. Our current is 90 milliamps. Now remember, milli is 1,000th. So 90 1,000ths of an amp. So 1/1000th is 0.001. So what we're going to do is we're going to translate this into amps, and 90 milliamps would be 0.090. Rearrange that formula. We're going to bring the 0.09 onto the other side of the equation. We're going to divide by that, and we'll get our resistance equaling 133.33. Since resistance is measured in ohms, our final answer is 133.33 ohms. In the exam, some questions may involve more than one equation. So when you sit the exam, there might be a question that's a bit longer and require the use of 2 equations, like V equals IR and Q equals IT. For the circuit above, calculate the charge delivered to the bulb after 3 minutes. Okay, so we know that V is equal to IR and we know that Q is equal to IT. Firstly, what we need to do is we need to try and find the current supplied. Because once we've found the current, we can then use the second equation, Q equals IT, to find the charge. So, V equals IR. 12 is equal to the current multiplied by 10 because our voltage is 12 volts, our resistance is 10 ohms. What is the current? Well, the current is 12 divided by 10 because we're going to divide both sides by 10. So our current is equal to 1.2 or 1.2 amps. Now we know the current, we can plug that in to this formula here. Q is equal to IT. So the charge is equal to 1.2 because that's our current that we have calculated, multiplied by 180. Why 180, I hear you ask? Because it's 3 minutes. 3 minutes is 180 seconds because there's 60 seconds in 1 minute. Times it by 3, you get 180. So the total charge delivered is 216. Charge is measured in coulombs, so our final answer is 216 coulombs. Complete task 6 in your electricity workbook if you are following along. Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backrowtutoring.com.